the last thing we have to do. Okay. Well, FTC Part 2 is how you evaluate definite integrals. FTC Part 1 is a part of the proof of that. Okay. And it's mildly interesting in its own right. So very quickly, let's assume that f is continuous where we care, as usual. Assume f is continuous where we care. And let's assume that a is a constant. Okay, a is some real number, it's a constant. All right. Then, what's this? All right. Then, what is the derivative with respect to x of the integral from a to x, right? A to x of f of t dt. All right. Now, actually, you can think of this as a function of x. This thing itself is a rule for a function of x. We can call it capital A of x. Why capital A? Because if you take a fixed value for x, okay, then what is this thing? It's a definite integral and it corresponds to a what? What do definite integrals correspond to? Basically, areas. Okay, yeah, constants, right? It's a constant. It represents an area or a sum of signed areas in general. All right. So what's sort of the idea here? All right. So let's say that the f function looks like this. All right. This time t here, t is our independent variable, our variable of integration. All right. Here's our constant a. All right. Let's say our constant, sorry, our variable x is here. Okay. Now let's say that we treat this as a function of x where x is variable. All right. Well, what are we asking here? If we assume for now that f is non-negative and continuous, all right, where we care, like around there, then for any fixed value of x, okay, where we have continuity, for example, all right, for any fixed value of x where we still have continuity, all right, what's going to happen is that this thing here is going to represent an area, a of x. All right. Bear in mind that as x changes, the area value changes. Okay. Now, what is this guy? Well, what is a derivative? It's a rate of change, right? It's a rate of change. So what this is basically asking is, how is the area changing? What is the rate of change of the area? Okay. So the derivative of a of x. All right. So what is the rate of change of the area? Okay, between a and x. All right. Well, according to FTC Part 1, it's very straightforward. It's just f of x. All right. It's just f of x, which is the function value. Okay. Intuitively, this makes sense because what is f of x? It's the signed height of this thing, right? The signed height of this thing. Now remember, this thing here represents the rate of change of the area. Now imagine this function keeps increasing, okay, up towards the heavens, all right? This thing keeps increasing, all right? When is this area changing more rapidly? If we're over here or if we're down there? When is it changing more rapidly as we go, as t increments by, say, 1 unit every second? Okay? We're going at a constant speed this way, all right? When is the area changing more rapidly? Over here or down there? When's it going to change more rapidly? Down there, right? Let's assume f is an increasing function, all right? So basically, the rate that this is increasing is contingent on this guy here, right? The signed height. Intuitively, that makes sense, all right? And the FTC Part 1 confirms that, and you can prove it, all right? That's in any standard. The proof is in any standard textbook, all right? Now, what's a homework problem here? Really, it's very straightforward. I like to say it's goo goo gaga. It's very easy. Okay. All right. Easy problem. Example. Okay. What's the derivative of the integral from 4 to x of t squared dt? All right. So this thing here is f of t. All right. F of t is t squared. And I'm telling you, folks, that the value of this is f of x. Well, if f of t is t squared, what's f of x? If f of t is t squared, what's f of x? X squared. So this is your answer. Right. So there is, in a sense, an unraveling, in a sense, okay? The idea that we're taking the derivative of an integral of something, all right, where we're integrating from a constant to this variable of differentiation, all right? That's what the FTC Part 1 basically gives us. Granted, the key application of this is that it's used to prove Part 2. Okay? That's why we did Part 2 first and emphasized Part 2 first. This is fair for your test, but at most it'll be like a 2 3-point problem or something. It won't be a big deal. All right. Questions? Questions? Just that bit to end. Part 6. The last section is not so bad because it's a continuation of that Riemann approximation stuff we did back in 5354.